We will now continue our discussion on the uniformly charged sphere in a cylinder. Remember that in part A we worried about this electric field created by this uniformly charged sphere, uh, and our cylinder is basically a hollow cylinder with radius greater than r, and it was non-conducting, carrying no net charge. So we wanted to find the flux through the side surface of the cylinder, and for that purpose we found the electric field created by the sphere for a radial distance r prime greater than the radius of the sphere r. So outside the sphere we found the electric field to be kq over r prime square, where k is Coulomb's constant, using Gauss law. And we finally got our result for the flux through the side surface. Now in part B of the problem, determine the electric flux upward through the circular cap at the top of the cylinder. So we want to determine the flux through the cap. So basically the flux through this region, the top cap. In part C, determine the electric flux downward through the circular cap at the bottom of the cylinder. So we will determine the flux through this cap. In part D, we will add the results from parts A to C to determine the outward electric flux through the closed cylinder, and then we will verify Gauss's law. Okay, so let's continue with part B. Now we have a radial distance square root of r square plus l square over 4 from the center when we consider a ring with radius r that is less than the radius of the cylinder, of the cylinder cap. The radius of the cylinder is capital R. Okay, so we're going to consider the flux through this circular region, and for that purpose we will consider an area element dA here, which is from the top view. You can see here, if we are at a distance r from the center, this distance is dr, this distance is r d theta, where theta is this angular displacement from the horizontal axis, and the area element is r dr d theta. So we find that the infinitesimal area is r dr d theta. And the electric field created by this sphere, which is uniformly charged to charge plus q, we have found in part A using Gauss law kq over r prime square, where r prime is the radial distance from the center. Now this r prime is, for this purpose, square root of r square plus l square over 4. So we find that the magnitude of the electric field must be equal to Coulomb's constant k, q, the total charge, divided by r prime square, which is r square plus l square over 4. All right, so because this is basically half of the length of the cylinder, L over 2 here. Here we have a right triangle, and our distance, radial distance to this ring is square root of r square plus l square over 4. Now this electric field, which is pointing radially outward from the sphere, actually has a component in the direction of the area vector. This area vector will be pointing in this direction, right? So this will be the direction of the area vector. This is the dA vector. So we need to consider E sine phi, where phi is this angle, and we can determine what sine phi is from this right triangle. Here it's L over 2 divided by the hypotenuse. All right. So we need to know the component of the electric field along the direction of the area vector, which is E sine phi, and that's going to be equal to the electric field magnitude we have determined using Gauss law, kq over r square plus l square over 4. This is the electric field due to the uniformly charged sphere. And then we have sine phi, which is capital L over 2 divided by r square plus L square over 4 square root. All right, so this is basically the component of the electric field in the direction of the area vector. The other component is perpendicular, so has no contribution to flux through this top cap. All right, now what is the flux d phi e due to this electric field? It is the perpendicular component of the electric field, E perpendicular, multiplied by dA, because then they are parallel to each other and cosine phi is 1. So if we substitute for the magnitude of the electric field, kq let's see here, we have kq L over 2, kq capital L over 2 divided by, or let's write it this way, kq capital L divided by 2, that is this part. And then we have r square plus L square over 4 multiplied by square root of that. And the area, the magnitude of the area is r dr d theta. And here at the bottom I have r square plus L square divided by 4 to the power 3 over 2. So this is E perpendicular multiplied by dA. That's our flux through this ring. Now what is the total flux? Total flux through the top cap. It's going to be kqL over 2, kq capital L over 2. Now I'm going to vary the angle theta from 0 to 2 pi and the radius from 0 to capital R, the radius of the cylinder. And I have to integrate over all such rings. So they each have area r dr d theta. And I have r square plus L square over 4 to the power 3 over 2 at the bottom. Now this integral, the theta integral, will just give me a factor of 2 pi. That's going to cancel this 2 and I will be left with a pi. So I will have pi kql, the integral from 0 to capital R, r dr, because I have already performed the theta integration, r square plus L square over 4 to the power 3 over 2. Now, in order to perform this integration, I'm going to let u square equals to r square plus L square divided by 4. Okay, with that, I will have 2u du is equal to 2r dr, and the 2's will cancel. So r dr will be replaced with u du. All right, so the cap flux pi e cap will be equal to pi kql integral. For r dr, I will substitute u du, and at the bottom I have u squared to the power 3 over 2, so I will have u cube. And this will be integrated between the minimum value of u and maximum value of u. So this is from u minimum to u maximum. And this is going to give me integral du over u square, which is a very easy integral, which is minus pi kq capital L 1 over u. So u to the power minus 1, if you differentiate it, gives you minus 1 over u square. So that's basically du over u square is what I'm going to obtain. So this will be evaluated between u minimum and u maximum. But instead of doing that and trying to find what those limits are, I will substitute for u. So minus pi kq over L, I have 1 over r squared plus L squared over 4 square root. That is what u is, right? Because u squared is r squared plus L squared over 4. And this will be evaluated between minimum value of r, 0, maximum value, capital R. All right. And now I'm ready to evaluate this. So if I substitute for r, capital R, I will have 1 over square root capital R squared plus L squared over 4. If I substitute 0 here, then I will have 1 over square root L squared over 4, which is 2 over L. And I also have a minus sign here. So let's switch these limits. So let's make this minus sign a plus. And then I have to change the limits. So this will be between capital R and 0. All right, so first I put 0. Let's see what I will get. The flux through the cap will be pi k q capital L. If I place 0 for R, I obtain 2 over L. If I place capital R, then I have 1 over capital R squared plus L squared divided by 4 square root. Or I can rewrite this result as the flux through this cap is, so if I multiply top and bottom with 4 epsilon 0, then I will have, because I have k is equal to 1 over 4 pi epsilon 0 here, the pi's cancel. I obtain q capital L divided by 4 epsilon 0, 2 over L minus 2 over r squared L squared plus 4r squared square root. So you see this is L squared plus 4r squared over square root of 4. Square root of 4 is 2. It comes upstairs, so it gives me this number. And here I have substituted for Coulomb's constant k 1 over 4 pi epsilon 0. So this is the answer I was looking for, the flux through this top cap. Now in part C, I was asked to find the flux through the bottom cap. That's going to be symmetric. So due to symmetry, the flux through the top must be equal to the flux through the bottom cap. So therefore, I will find that I have the same answer. Flux through the bottom is also equal to Q capital L over 4 epsilon 0, 2 over L minus 2 over L squared plus 4R squared square root. The same answer. In part D, we were asked to find the total flux. The total flux through the cylinder is basically the flux through the side surface plus twice the flux through the top cap or the bottom cap, because they are the same. So let's see what we get here. The flux through the side, that's the answer to part A, is QL over epsilon 0 square root L square plus 4 capital R square. So let's see Q over epsilon 0 I have an L also, QL over epsilon 0. I have 1 over L square plus 4R square square root. Then I have twice this flux. So if you can see here, if I take this 2 outside, this would be 1 over 2 epsilon 0. If I multiply it by 2, I will also have QL over epsilon 0 here. So this will give me plus 1 over L minus 1 over L square plus 4R square square root. This is what I obtain when I multiply it by 2. So there's a factor of 2 here. There's a 2 here, so that cancels this 4. So I have QL over epsilon 0. This comes from the side flux, and this comes from the top and bottom caps. Now you can see that these two will cancel out, and I will be left with the total flux, phi total equal to capital Q divided by epsilon 0. Now in part E, we were asked to verify Gauss law. According to Gauss law, the total flux is the charge enclosed by the surface divided by epsilon 0, which is capital Q divided by epsilon 0. So we find that our result agrees with Gauss law. Okay, so in this problem we have considered, to summarize, a uniformly charged insulating sphere carrying a charge Q, radius R, at the center of a hollow cylinder with radius capital R greater than R and length L greater than 2R. The cylinder is non-conducting and carries no net charge. So for the side surface, we have considered the area 2 pi capital R dz. That's the infinitesimal area through the side surface. And we have considered the electric field going through the side surface. And we've taken the component parallel to the area vector. So that's E cosine theta multiplied by dA and integrate over the full length to obtain the total flux. And that's what we have done here. And in part B, we have considered the electric flux through the top cap first. There, the infinitesimal area is R dr d theta, where we have the radial electric field pointing in the radially outward direction due to this uniformly charged sphere. And then we have considered the component of the electric field in the direction of the area vector, where dA magnitude is R dr d theta. So the electric field magnitude multiplied by sine phi, which is L over 2 divided by square root of R squared plus L squared over 4. And then we integrate over all possible angles to cover the ring and all possible radii to cover the full area of the top cap. And there we have found this answer, and this answer is identical to the answer we would find for the bottom cap due to the symmetry of the problem, so we have the same result. If we add the contribution from the side surface and the top and bottom caps, we obtain the total flux to be capital Q over epsilon 0. What is capital Q? If you consider this a Gaussian surface here, this is enclosing a total charge Q. Therefore, the flux through this surface, cylindrical surface, should be capital Q divided by epsilon 0, permittivity of free space. That's indeed what we find by adding the flux contribution from all sides.